ஹலோ. நம்மளே ஆமாம் ஆமாம். ஓகே. அதில் தான் சார். பரவாயில்ல அட்மிட் பண்ண. ஓகே சரி ஓகே. சரி ஓகே. ஓகே.
என்ன செய்யணும்?
போயிட்டு இருக்கேன். மெயிலை எத்தனை பேர் பார்த்து இது பண்ணுன்னு தெரியல. பார்ப்போம்.
உங்கள் சார் வந்துட்டாரா?
சார் குட் ஆஃப்டர்நூன் சார்.
குட் ஆஃப்டர்நூன் பாலகுமார்.
வீட்ல
தானே?
இல்ல சார், வீட்ல இருக்கேன். ஜஸ்ட் கேம் ஃப்ரம் ஹோம் டவுன்.
ஆபீஸா? சரி சரி, ஹோம் டவுன்ல இருக்கா? சரி.
ஆமா, காலையில சார் வந்தோம். சரி அதான்
எப்படி இருக்கு உங்க ஊர்ல எல்லாம் கோவிட்?
கோவிட் அங்கெல்லாம் ஒன்றும் பெருசா தெரியலைங்க சார்.
சரி, சென்னையில தான் பெருசா இருக்கா?
சென்னையில பயமுறுத்தி இருக்கிறாங்க, பட் நாட் ஷூர் ஹவு ஃபார் இட்ஸ் ட்ரூ. அண்ட் ஏன்னா டெஸ்டிங் தான் இன்க்ரீஸ் பண்ணிருக்காங்க. இப்ப டெஸ்டிங் 14 நாள் கழிச்சு தானே பண்ணிருக்காங்க. டெஸ்டிங் போட்டதுனால அதிகமா இருக்கு.
நீங்க ஒண்ணு கிளீனாவே தெரியல பிக்சர். ஆக்சுவல் டேட்டாவா என்ன ஏது
தெரியலைங்க சார். பட் டெத் ரேட் காட்டுறானே சார். டெத் ரேட்டை காட்டுறானே.
முடியல. இப்போ இந்த 45 வயசு மேல உள்ளவங்களுக்கு எல்லாம் ஊசி போட சொல்லியிருக்காங்களா?
ஆமா ஆமாங்க சார். இப்பதான் கார்பரேஷன்ல இருந்து வந்துடுறாங்க. ஏன் ஊசி போடுறவங்க கேள்வி கேட்கறாங்க.
சரி சரி. உங்க தமிழ்நாட்டுக்குள்ள 2 வீக்ஸ்க்குள்ள போட சொல்லியிருக்காங்க.
ஆமாங்க சார். ஆமாங்க
மாசிவா வந்து பண்ணுவாங்களா இருக்கும். சரி பாப்போம் எப்படி இருக்குன்ட்டு.
ஓகே சார்.
வேற என்ன?
ஒரு 3 o'clock ஆரம்பிச்சாங்களா சார்? 2:55 போல வந்துருவாங்க.
நோ
350 ரைஸ் பண்ணிருக்காங்க.
சரி ஓகே.
Waiting for NCNS container.
டக்குன்னு கிடச்சி ஈஸியாக இருக்குது. அந்த லிங்க் ஒரு சில இடத்துல
சார் ஸ்லைட ஷேர் பண்றீங்களா சார்?
அது எப்படி அதாவது இது வரல எனக்கு.
இல்ல பிரசன்ட் நவுன் ஃபைல்ல இருக்கும் பாருங்க சார்.
பிரசன்ட் நவ் அதுல போறேன். விண்டோவா
அது விண்டோ கேக்குது சார்.
அதுல வந்து செலக்ட் விண்டோ, அதுல வந்து will you allow me to see your screen, window or screen to share, select window or screen. அது செலக்ட் பண்ணணுமா?
ஏன் விண்டோ இருக்கு பாத்தீங்களா சார்?
ஆமா,
அத செலக்ட் பண்ணிக்கோங்க சார். அங்க போனா பிபிடி நீங்க யூஸ் பண்ணிக்கோங்க.
எனக்கு வரலையே. அதான் இப்ப ஏதாவது தெரியுதா?
இப்போ வந்து நீங்க என்ன பண்ணிக்கீங்கன்னா இதே விண்டோவை நீங்க ஷேர் பண்ணிருக்கீங்க இந்த டெஸ்க்டாப்ல இருக்கிற கூகுள் விண்டோவையும். சரிங்களா சார்? நீங்க பிரசன்ட் நவுல போய் ஏன் விண்டோ இருக்கும், ஏன் விண்டோ இருக்கும், சரி பண்ணீங்கன்னா ஆப்ஷன்ஸ் வரும்.
ஆப்ஷன்ஸ்ல
பிபிடி இருக்கும். பிபிடி ஓபன் பண்ணிட்டீங்களா?
என்டையர் ஸ்கிரீன் போறேன்.
இல்ல என்டையர் ஸ்கிரீன் வேணும். அது கீழ கரை வந்து விண்டோ இருக்கு பாத்தீங்களா?
ஆமா,
விண்டோ கிளிக் பண்ணீங்கன்னா நீங்க பிபிடி ஓபன் பண்ணி வச்சீங்கன்னா அந்த விண்டோவை காட்டுது.
ஓகே, ஜஸ்ட் ஐ வில் டு இட். ஓகே Okay, now yours. You can see.
வந்துருச்சு சார். யா. டைம் எடுக்குது. இப்ப ஸ்லைடு மோடுக்கு வந்துருக்கு சார். சேவ் ஃபைல் பண்ணீங்கன்னா போதும்.
போதும் இல்லையா?
F5 பிரஸ் பண்ணிட்டீங்களா?
F5 போட்டு லைட் தானே வருது.
இல்ல ஸ்லைடு மோடுக்கு போங்க சார். கீழே போய் அந்த இது ஸ்லைடு மோடு இருக்கும்ல, கீழே ஒரு இது
டிரான்சிஷன்ஸ் ஸ்லைடு மோட் போட்டேன். இத நான் மேனுவலாவே ஆன் பண்ணிக்கிறேனே, மூவ் பண்ணிக்கிறேனே.
பண்ணிக்கலாம் சார். நீங்க இந்த ரைட் சைடு க்ளோஸ் பண்ணிட்டீங்கன்னா இந்த லெஃப்ட் சைடு உங்களுக்கு இருக்கு இல்லையா இந்த சைஸ் அதை க்ளோஸ் பண்ணா விண்டோ கொஞ்சம் பெருசா வரும் சார்.
இதுல எதை க்ளோஸ் பண்ண
இல்லை சார், இப்ப வந்து சின்ன பெரிய ஸ்கிரீன் நீங்க பிரசன்ட் சைடு வந்து சைடுல சில ஸ்லைட்ஸ் இருக்கு இல்லைங்களா சார், இப்ப ராமன்லாம் சார்ல.
ஆமாமா,
அதான் அந்த இதை நீங்க மினிமைஸ் பண்ணலாம். மினிமைஸ் பண்ண ஸ்லைடு கொஞ்சம் பெருசா வரும்.
ஓ உங்க இதையா?
இல்லைங்க சார், இப்ப இந்த பக்கம் ராமன் இந்த பக்கம் இந்த ஸ்லைட்லாம் இருக்குங்களா?
ஆமா. ஓ சரி. ஆமா. ஓ சரி.
அதை க்ளோஸ் பண்ணீங்கன்னா ஸ்லைட் கொஞ்சம் வந்து ஃபுல் ஸ்லைடு இந்த எடுத்தாங்க.
ஓகே. இல்ல ஒரு நிமிஷம், நான் அந்த வேற ஸ்லைடு ஆக்சுவலா க்ளோஸ் பண்ணிட்டு ஓகே.
அது ஒரு பிரச்சனை இல்லை, நான் இருக்கிறது சொல்லிட்ட மகளே.
இல்ல
ஆமா ஆமா, இல்ல அது என்னோட தான், அவ்வளவுதான். ஓகே ஓகே ஓகே, அவ்வளவுதான் ஒண்ணு. கேட்டாங்கன்னா சொல்லுங்க, அந்த வீடு ரன் பண்ணி வச்சு சாரோட வீடு வந்துட்டு அவங்க சொல்லிட்டாங்க, அவ்வளவுதான்.
இப்ப எப்படி இருக்கு இது?
இப்பதான் வருது. ஓகே சார், இப்பதான் வருது. Let it very slow. Yes sir. இப்ப நீங்க ஸ்லைடு மோடுக்கு போட முடியாதா சார்?
ஸ்லைடு மோடு தான், ஒரு நிமிஷம்.
ஜஸ்ட் F5 பிரஸ் பண்ணுங்க சார்.
இதான் போட்டேன். ஸ்லைடு மோடு டிசைனர் ட்ரான்சிஷன். ஸ்லைடு மோடு தான் போயிருக்கேன், ஸ்லைட் மோட்ல தான் இருக்கேன்.
சரிங்க சார், ஓகே சார், நம்ம அப்படியே ஆரம்பிச்சுக்கலாம் சார், ஒன்றும் ப்ராப்ளம் இல்லை. ஸ்டார்ட் பண்ணலாமா சார்?
ஓகே ஸ்டார்ட்.
Very good afternoon and welcome to the Nanomaterials Characterization lecture series, and this is organized by our National Center for Nanoscience and Nanotechnology. On behalf of the center and on my own behalf, I welcome our teacher, Dr. Ramakrishnan sir, former director ISAP Trivandrum, and presently sir serving as a UGC BS fellow, School of Physics and Madurai Kamaraj University. Sir has a long experience in both in academics and administration. He joined as a lecturer after his PhD in 1987 in School of Physics Madurai, and then he promoted as a reader and professor and professor in 2019. And also he became a senior professor in 2019. And generally, getting a senior professor is not easy in the university, and he is one of the main person who got elevated to senior professor. And also he served as a School of Physics chairperson from 2013 to 2014. And later he joined 2014. He joined as the director for Engineering Science Foundation and Research. Trivandrum, and also served as a mentor and director for Indian Institute of Information Technology. There are also, I mean, he's worked at various levels as a program coordinator, UPE and the first program, and the member senate and academic services. Served in various level in the university, and also he worked in. He visited many countries. Particularly, he visited federation arrangement with the International Center for Verification Science Italy, and then he's also worked as a Commonwealth Academic Fellow from 2007 to 2008 in the UK, and also he worked as a SBBL researcher at the University of Electronic Communication, Tokyo, Japan, and he's also taken a JSPS fellowship, one of the prestigious fellowships. Such an eminent person is with us, and he has published more than 150 papers in a reputed journal, and is one of the very good administrators. And apart from that, he's a very nice person, and always very much interested to discuss physics and science all the time. That's how I know him for the past 2 years. So such an eminent person is agreed to give a lecture for our students. That's the reason I actually opened this the forum for all the students, those who are interested to learn grammar spectroscopy. With a small introduction, I welcome our Ramakrishnan sir to deliver the lecture on novel spectroscopy studies for material research. The floor is yours, sir. Okay, sir.
Good afternoon, Professor Balkumar. Thank you very much for your nice introduction. I'm really very happy to meet the students in online mode because for an academician it is very difficult to keep idle, because always he has to share or he has to discuss science. So this is the field I am working for the last maybe for nearly 40 years. So I joined as a PhD student in 1983 at the University of Kerala. So I have been working on this field for a very long time.
Sir, connection cut ஆயிடுச்சு சார்.
Connection இப்போ
ஸ்லைடு வரலீங்களா சார்?
எனக்கு ஓப்பனா இருக்கேன்.
Present now னு போய் மறுபடியும் பண்ணுங்க சார்.
பண்ணவா? Okay. This is Professor C.V. Raman's photo. You can see he has mentioned that fundamental science cannot be driven by instructional, industrial and government or military pressures. It has to be an intuitive one. People should have an attitude and then aptitude for it to do fundamental science. That is to try to understand why it happens, what happens, what's the mechanism behind it, what is the physics behind it, whether you have understood it conceptually. So all these things cannot be driven by instructional or industrial. It has to come from the individual's attitude. நிக்கிற ஸ்லைடு
அது அப்படியே ஒண்ணு சார் மூவ் பண்ணணும். கூகுள் வந்து பேண்ட்விட்த் கொஞ்சம் நம்ம பிரசன்டேஷன்ல பேண்ட்விட்த் கொஞ்சம் ப்ராப்ளம்
இங்க
நிக்கிது அப்படியே நிக்கிது.
எனக்கு வேற ஸ்கிரீன் சேஞ்ச் பண்ண முடியல. என்னோட ஸ்கிரீன்ல இப்ப ஷேர் ஆயிட்டு இருக்கு.
Okay. Raleigh was the first to explain blue color of the sea. He says color of the sea is simply a reflection of the sky's color. The sky is blue because that is the scattering of light in the water particles. But the sea looks blue because a reflection of the sky's color. That was Lord Raleigh's explanation. But in 1921, Professor C. Raman, he was attending the Congress of Histories of the British Empire, where he was looking at beautiful of the sea as on deck, and he was having a key small kit consisting of a prism, a small microscope, and a diffraction grating, maybe some polarizer, analyzer combination. but because when you rotate the polarization, analyze the combination,
லிங்க் கிடைக்காம இருக்கும்னு தெரியல.
analyze the combination, you could see some
mail
variation
வந்து
in
நான் ரெஸ்பாண்ட் பண்ணேன்.
the intensities. Then is that the
ஆமா.
color of the sea is due to the scattering of light, not by the reflection.
Okay. In case
So he says that it
mail
is not
பண்ணா
totally
நான் அதே
correct.
மாதிரி response
So on
பண்றேன்.
returning to his laboratory, he worked on a problem on that scattering of light. So there he continues. So February 28, Tuesday 1928, Professor was there and he proceeded to examine the influence of the wavelength of the incident light on the phenomenon. On examining the track with a direct vision spectroscope, we found to great surprise that the modified scattering was separated from the scattering corresponding to the incident light by a dark region. So they could see both high frequency shifted Raman line and the low frequency shifted Raman line. So the Raman effect had been discovered. A newspaper announcement was made on the following day. 29 was a leap year because it's a leap year. So they published a paper in Nature. Then got the Nobel Prize. To commemorate the legacy of C.V. Raman, 28 February has been designated as the National Science Day. So this is the extract of the cable from Nature, Professor R.W. Wood. It appears to me that this very beautiful discovery, which resulted from Professor Raman's long and patient study of the phenomenon of light scattering, and it is one of the most convincing proof of the quantum theory of light. So this is a book which tells Journey into Light, Life and Science of Professor C.V. Raman by Professor G. Venkatraman, published by Indian Academy of Sciences. In fact, I could not get the copy. Since I was the director of the National Institute, I could get a copy. Maybe it was slightly torn on here and there. There was also another interesting work done by Professor Raman, that is Raman-Nath diffraction, that is acoustic effect. But many people may not be knowing, but people who are studying optical electronics or optoelectronics or lasers, IMTech lasers, they will be knowing what is acoustic effect. It is one of the greatest contribution of Professor Raman's student. What you see, this one is the old Raman spectrometer which he has used, and this is the instrument which I have used for my PhD days in 1980s. And now this is a micro Raman setup which we have started to use from 2005. Pardon?
The slide move ஆகுங்க.
எனக்கு மூவ் ஆகுது.
அந்த ஸ்லைடை மட்டும் நீங்க கிளிக் பண்ணுங்க. The bandwidth issue அந்த மாதிரி we will have this issue.
இப்ப தெரியுதா?
இல்ல இது still be on the relapse one third side இருக்கு.
Oh.
No sir, no sir. No.
இப்போ
இல்லைங்க சார், இல்லைங்க சார்.
வெளியில போயிட்டு வரவா?
வெளியில வேணா போயிட்டு வாங்க சார். ரைட் சார்.
सर F5 प्रेस कर दीजिए ना तो प्रेजेंट हो जाएगा.
No, it's not a problem with the F5. It's a problem with the slide because the bandwidth issue and that could be another issue.
सही है सर, ट्रांसलेट ही नहीं हो रहा है.
Yeah. Just give us a minute and we will do.
இதை வந்து அந்த எல்லா இது கொடுத்தோம்.
Now
slide has come there, but usually the first thing is very detailed.
இப்போ மூவ் ஆகுதா?
இல்ல still in the first slide. நீங்க just click the particular side click பண்ணி அங்க போகுங்க.
இப்போ
no நீங்க slide mode ல வச்சிருக்கீங்களா சார்? F5 press பண்ணி
F5 இங்க போட்டு மா
இல்ல just you press F5, you go to the slide mode, presentation slide mode.
Hello. मैंने லேபிள் தான் இருக்குது
ensured transitions. Okay, slide show. Slide show.
சரி
இப்போ
No, sir.
இப்போ நோவா.
Bandwidth is very low. That's not problem with the system, sir. It's the problem with the bandwidth.
இப்போ நான் என்ன பண்ண சொல்லுங்க?
நீங்க அந்த ஸ்லைட் மூவ் பண்ண முடியா பாருங்க சார் ஒவ்வொரு ஸ்லைட். நீங்க ஸ்லைட் மோட் போகாமலே மூவ் பண்ணலாம். I used to take class like that.
இப்போ தெரியுதா?
Still in the first slide, sir.
அது எப்படி?
சார் உங்க இமெயில் இருந்தா குயிக்கா எனக்கு அனுப்பிச்சு விட்டுருங்க. நான் I will present the slide.
Okay, no problem.
ശരി മാം ഞാൻ ഓക്കെ ഞാൻ വിളിക്കാം മാമേ ഒരു പ്രോഗ്രാം ഒന്ന് ഓടിയിട്ടിருக்கு ഞാൻ ഫോൺ பண்ணுறேன் ഞാൻ முடிச்சதும் ഫോൺ பண்ணுறேன்.
Sorry students, please bear with us if it takes few minutes because we have some problem in the network.
ஓகே சரி.
ஆக்சுவலா அது ஒரு நிமிஷம் பாலகுமார் அதை பிடிஎஃப்ல கன்வெர்ட் பிகாஸ் அது மெமரி ஹெவியா இருக்கு.
நீங்க பிடிஎஃப்ல கன்வெர்ட் பண்ணா கூட it would be better.
Just a minute, Balkumar, I will come.
Yes, sir. Please. Students, please bear with us and let us use some time for staff to convert in PDF so that your presentation will be good.
Yeah. இப்போ பிடிஎஃப்
இது பிடிஎஃப்ங்களா இல்லையே?
இல்ல நான் பிபிடில இருக்கு. நான் ஸ்டில் சீக்கிங் ஹெல்ப். ஓகே
யா
ஓகே, இது டெஸ்க்டாப்ல போகலாம் இல்லையா? பப்ளிஷ்னா
Individual mark లేదన్నా number group நம்மளால எல்லாத்தையும்
ஓகே, இது வந்துருச்சு இல்லையா? ரைட், தேங்க்யூ. சொல்லுங்கம்மா, நான் உங்களுக்கு மெயில் அனுப்பியிருக்கேன். சொல்லுங்கம்மா. சொல்லுங்கம்மா.
Yes, sir. I just received it and just downloading it.
ஓகே, நான் அப்படியே அந்த ஸ்லைடை பார்த்துட்டு நான் சொல்லிட்டே வந்துடலாம் இல்லையா?
Yeah. No issue. சார் இப்ப ஸ்லைட் வருதுங்களா?
இங்க உங்க இதுல பாக்கலாமாண்ணா? ஓகே, ரைட். நவ ஐ கேன் see. இப்போ இதுல எப்படி மூவ் பண்றது?
நீங்க தான் சொல்லணும். உங்க சைடு நெக்ஸ்ட் ஸ்லைட் சொன்னா மூவ் பண்ணுங்க.
ஓகே, the next slide.
Yeah.
The next slide. Oh, next. Okay, this is okay. So this what you see here. This is if I move mouse, they could see it or not? No, they cannot see, isn't it? So
நீங்க பேச sir, you can just talk sir, I can move. That's it.
okay, what do you see on the left side? There is an old instrument that is a Raman spectrometer, which is in the first floor of IIC Bangalore administrative building. This is an old instrument which Professor Raman used. What do you see on the right top? There is a single grating monochromator. That is a dispersive monochromator which I have used. That is the instrument which has been used from 1980s. And what you see here at the down is the micro Raman spectrometer, which is available from 2000 onwards, but we have started use from around 2007 or 2008. Next slide. Yes, sir. Okay, so these are the two people. I know one is Professor K.S. Vishwanathan. He was the head of the Department of Physics, University of Kerala. He worked with the Professor C.V. Raman. In fact, I was fortunate to work under him. And another is Professor P.S. Narayanan. He was also a student of Professor C. Raman. He was a professor at the University of Science, Bangalore. I worked with him as a short-term research worker in 1985. Next slide. Okay, symmetry. The impacts of symmetry is on physical properties, on molecular reactions and molecular vibrations. Group theory is nothing but behavior of molecule based on the symmetry. What you see is Taj Mahal and is another beautiful building. If you look at both buildings are very high, both of them have a higher order mirror symmetry. If you look at what is in the Taj Mahal, what you see on the left side, you can see what is on the right side. It's a perfect, it has a mirror symmetry. Like that, what you see on the right side, that building also has a higher mirror symmetry. Next slide. So symmetry operation is nothing but an action which a molecular operation, that is, the molecule is not unchanged. Action by which the molecule symmetry is not disturbed. That it can be a rotation through an angle or a reflection by a mirror plane. And a symmetry element is nothing but the location of a symmetry operation. It can be a point, it can be a line, it can be a plane. Point group symmetry is nothing but a set of symmetry operations which leaves at a particular point unchanged in the molecule. So this point, which is being unchanged because of this operation, this point can be an atom or it can be an imaginary point. The identity operation, E, it is an operation which does not do anything, which leaves the object unchanged. Just like you have a H2O molecule, after the identity operation, it just remains the same. There is no rotation, no reflection, like that. Next slide. If you have a water molecule, it has n-fold symmetry axis that you see with the suffix n. Suppose you have a 360 degree, that is 2 pi by n. So if you rotate twice, that is, if you rotate twice, that with the oxygen atom and two hydrogen atoms, an axis passing through the oxygen atom, bisecting the angle between HOH, and rotate 190 degree, the two hydrogen atoms are interchanged. Then again you do 190 degree, the hydrogen atoms come to their original positions. For if we rotate 180 degree, the molecular configuration is not changed and it remains the same. After 360 degree, it comes back to the original position. So you have rotated twice, but each time you rotate 180 degree. Next slide. So you have mirror planes. That is, a molecule can have different types of mirror planes. There is a vertical mirror plane and a horizontal mirror plane and a dihedral plane. This is a vertical mirror plane. See, you have a water molecule. So there is a mirror plane bisecting the HOH angle. So two hydrogen atoms are exchanged. Then, because two identical atoms are exchanged, still after the reflection, the molecular configuration is not changed. Only this H1 goes to H2 and H2 comes to H1, but both of them are identical atoms, so the molecular configuration is not changed. Next, please come down. So there is a just above it. Previous slide. Okay. So there is a horizontal plane. That is, all the atoms are lying in the same plane. So in the first case where I told vertical mirror plane, there is a mirror plane which contains the principal axis of rotation. And the sigma horizontal plane is a mirror plane which is perpendicular to the principal axis of rotation. So there are two types of rotation. One is a mirror plane which contains the principal axis of rotation, like the C2 axis in the water molecule, and a sigma horizontal plane which is perpendicular to the principal axis of rotation of the benzene molecule, which is a C6 molecule. And a sigma dihedral mirror plane is a mirror plane, again contains the principal axis of rotation, but it lies between the two-fold axes. So benzene is a case where you have sigma dihedral planes, sigma vertical planes, and sigma horizontal planes. Next slide. Next slide. Okay, inversion center. So center of inversion, that is a reflection through a center of molecule and equal distance on the opposite side. Suppose you have a carbon dioxide molecule. So you have one oxygen is along the y-axis, positive y-axis, another oxygen is along the negative y-axis. So the first oxygen will have the 0, y, z. Another one is 0, minus y, z. Minus y, z. So that is, if you have an atom with x, y, z coordinate, there will be another identical atom with the coordinate minus x, minus y, minus z. So if you look at this molecule which is shown in the bottom, you have all the atoms will have their corresponding atoms with the coordinates minus x, minus y, minus z. So In this case, there is an imaginary point in which all the atoms goes to their negative positions. That is, x, y, z goes to minus x, minus y, minus z. Or if you have x1, y1, z1, it goes to minus x1, minus y1, minus z1. So if that is the case, then this molecule has inversion symmetry. The next slide. Wait, okay. This is not necessary. Next slide. Okay. Next slide. So point groups is nothing but it's based on the symmetry operation possessed by the molecule. So there is a strong relation between the molecular symmetry and the point. There is a molecule which is a carbon dioxide, which is a linear molecule. So you have oxygen atoms symmetrically well placed. Previous slide. But HCN molecule is a linear, but there is no symmetry. And then there is a CH4 methane molecule which has a higher order of symmetry. There is a tetrahedral symmetry. And SF6, this is a octahedral symmetry. And the benzene, you have a D6H symmetry. So these are the very classical examples where a point group symmetry can be classified depending upon the number of symmetry operations in that system. Next slide. Next slide. So what a point group is? C2V, because it has an identity element, two-fold axis, two sigma vertical planes. Ammonia, it has it belongs to three C3V point groups, and it has two three-fold axis and three sigma V planes. That is two C3 axis, three sigma vertical planes. So water belongs to C2V point group, and ammonia belongs to C3V point. Next slide. Next slide, Palakma. So just I said benzene D6H. Suppose just you remove one hydrogen and put with a chlorine, then the total symmetry is reduced. It goes from the D6H point group to CS point. So that is where we have to understand how the molecular symmetry can influence molecular vibrations. So now higher order symmetry D6H unsubstituted benzene goes to a very lower order symmetry, that is CS symmetry, just because one hydrogen is replaced by one chlorine. Previous slide. Now you say that symmetrically I place another chlorine. Previous slide. Previous. Now in this case it belongs to C2V point. So in one case, when there is unsubstituted benzene, it belongs to the higher order of symmetry, that is D6H point group. With just one chlorine substitution, it goes to CS point group. Now two chlorines are symmetrically placed. Now it belongs to C2V point. So this is the case where when the molecule symmetry is reduced because of intermolecular interactions, when the molecular symmetry is reduced because of the intermolecular interactions, one can look at it which type of point group symmetry it has. So when you look at the Raman spectrum, I will just explain some cases. Next slide. Next slide. Next slide, please. So this is a chiral molecule. You can see that it's a left-handed, right-handed system. So this left-handed, right-handed system, they always influence molecular reactions, optical activity, that all will be reflected in the vibration spectroscopy. Vibration spectrum. Next slide. Next slide. Next slide. Next slide. Okay. So this is what spectroscopists look at it, character table. So if you want to know that your molecule has common active vibrations, first of all, you should understand what is its symmetry, that is your point group symmetry. Once you know the point group symmetry, you can have the standard character table. That is what I am showing here, a standard character table. So that's all available. So once you know the character table, now you can say that which species are Raman active, which species are infrared active. So A1 species, they are all X square, Y square, Z square, they are all Raman active. A2 species, this is Raman active. B1 species, Raman active. B2 species, Raman active. whereas A1 species is infrared active, B1 species is infrared active, B2 species is infrared active. So first of all, that's why I said first you must know your molecule. Once you know the molecule, you must know what's its point group symmetry. To understand point group symmetry, you must know the symmetry operations. So once you know the symmetry operations, you will elucidate the points group symmetry of your molecule. Once the point group symmetry is known, you have the standard character table. From the character table, you can identify which are the species Raman active, which are the species infrared active. Next slide. Next slide, please. So spectroscopy is nothing but the interaction of the electromagnetic radiation with matter that helps you to understand atomic and molecular structure. The energy of the molecule, there are three classifications: rotational, vibration, and electronic. Transition between electronic states will give you the electronic spectroscopy. Transition between rotational states will give you microwave and far infrared. Transition between vibrational states will give you the vibrational spectroscopy. Next slide. So then we have to understand what is normal modes of vibrations. The normal modes of vibrations, first of all, you know how a molecule has how many number of degrees of freedom. So the degrees of freedom for a particular molecule depends upon the number of atoms. Suppose there are n number of atoms, there are 3n degrees of freedom. That is, you can describe the molecule in a 3n in different ways. That is a 3n degrees of freedom. So the 3n independent ways by which you can describe the molecule. So among the 3n degrees of freedom, 3 corresponds to the translational motion, 3 corresponds to the rotational motion. So among the 3 translation, if it is a linear molecule, the rotation about the bond axis, 3 translation and 3 rotation. Among the rotations, the rotation about the bond axis do not contribute for a linear molecule. So if it is, previous slide. So if there is a non-linear molecule, there are 3n minus 6, previous slide. Sorry, this, next slide. Okay. In a non-linear molecule, there are 3n minus 6 normal modes of vibration. That is 3 into n minus 6. The 6, among the 6, 3 corresponds to the translational motions, 3 corresponds to the rotational motions. For linear molecule, 3n minus 5. The 5 and 2 rotational motion. That is, the rotation about the bond axis do not contribute. So if you have a non-linear molecule like water, next slide. If it is a water molecule, it's a non-linear molecule. So 3 into 3 minus 6, 9 minus 6, so there are 3 normal modes of vibrations. So the 3 normal modes of vibrations mean there are 3 independent ways by which the molecule vibrate. There are 3 independent ways by which the molecule vibrate. During the vibration, the bonds may be extended or compressed, or the bond angle may be changed. So the symmetric stretching is the one in which the bonds extends symmetrically. The both hydroxyl OH bonds are expanded or extended or compressed symmetrically with respect to each other. And the symmetric bend, the bond angle is changed periodically. That is, the HOH angle is changed periodically. And the antisymmetric stretch, one OH bond is extended, another OH bond is compressed. So that is called antisymmetric stretch. So one is extension, another is compression. So that is antisymmetric stretch. So you have a symmetric stretching vibration, you have a symmetric bending vibration, and antisymmetric stretch vibration. So each vibrations have 3 different frequencies. Symmetric stretch has 3652 wave number, and a symmetric bending has a frequency 1595 wave number. Antisymmetric stretch has a frequency at 3756 wave number. Carbon dioxide is a linear, so it has 3n minus 5, 4 normal modes of vibrations. So you have a symmetric stretch, antisymmetric stretch, and a bend. The bending vibration is a doubly degenerate vibration. So one is non-degenerate, another is symmetric stretching is non-degenerate, antisymmetric stretch is non-degenerate, but bending vibration is doubly degenerate. So 1 plus 1 plus 2. So totally 4 normal modes of vibration. Next slide. So Raman spectroscopy is nothing but inelastic scattering of light. It is a non-destructive optical tool, and the Raman shift is very important. It does not change with the excitation frequency. It is the characteristics of the particular molecule. The Raman shift or the wave number tells you the chemical bonding and the structure, inter and intramolecular interactions. All the spectral features, all molecular features can be deduced from the spectral wave number. And the bandwidth, the spectral bandwidth of the Raman line, it tells about the molecular dynamics. Next slide, please. We can just pass to the next slide. Next slide. Okay, so this is we have two vibration levels. Infrared absorption, it goes from V0, V is equal to 0 to V is equal to 1. And the Rayleigh scattering, that is h nu 0 is the incident, and the emitted photon is also h nu 0, or we call it the scattered photon. And then the Stokes scattering, the incident photon is h nu 0, the scattered photon is h nu 0 minus h nu m. That's the energy difference between the two vibration levels. That is subtracted from the incident photon. Anti-Stokes scattering, the incident photon h nu 0, the scattered photon is h nu 0 plus h nu m. The scattered photons has an energy difference corresponding to the energy between the two vibration states. Here the energy is added up, here the energy is reduced. So the Stokes scattering has a lower frequency, and the Stokes scattering has a higher frequency. So as you think, because the Stokes scattering originates from the ground state, so the Stokes lines are always indexed, whereas the anti-Stokes scattering, which starts from the excited state, the V is equal to 1 state, so that where the population level will be less compared to V is equal to 0. So the anti-Stokes scattered photons will be, number of anti-Stokes scattered photons will be less, or the Raman lines for the anti-Stokes scattered will be less. Next slide. So the Raman lines, always they say the depolarized lines. So the degree of polarization of the Raman line is very important, and it tells about the anisotropic character of the system. So if you have y-axis is the direction of the incident beam, and x-axis is the direction of the scattered beam, and this arrow which tells the state of polarization of the incident beam. And if you have the scattered direction, you have the analyzer which is parallel to the z-axis, and you can have the analyzer parallel to the y-axis. So if the analyzer axis is parallel to the z-axis, then that is why I put ZZ, that is the intensity is measured parallel. That is the analyzer axis is made parallel to the state of polarization of the incident beam. Here the analyzer axis is perpendicular to the state of polarization of the incident beam. That is Z, why the first Z tells the state of polarization of the incident beam. Second word alphabet tells about the analyzer direction. So here ZZ is the parallel, ZY is the perpendicular. So rho is nothing but I perpendicular by I parallel. The intensity measured when the analyzer is perpendicular, analyzer axis is perpendicular to the state of polarization of the incident beam. Here analyzer axis is made parallel to the state of polarization of the incident beam. I perpendicular by I parallel. So for this is a typical case of carbon tetrachloride, where in which I perpendicular is almost 0 for the 459 Raman line, whereas other lines it will be slightly less. So if you measure the ratio, the I perpendicular by I parallel, rho theoretically is 0. That is the ratio between the I parallel and I perpendicular is 0 in the case of carbon tetrachloride molecule. It says it's a totally symmetric stretching vibration. So in this all cases, what you have seen is the wave number position is not changed. Either you measure in I perpendicular this, or you measure in a I parallel positions. Either I perpendicular or I parallel, the wave numbers are shifted. They remain the same. Next slide. Next slide. Next slide. Okay. Now this is a simple case. Now you have Na2HPO4 2H2O. This molecule, this crystal, it crystallizes in BBCA or D2H15. That also I will say BBCA. What is D2H? I will tell you later. In the next slide, next material I will tell you. Disodium hydrogen phosphide dihydride. Okay. In this case, the extracrystallographically data says that there are two water molecules which are crystallographically non-equivalent sites. So this is one HPO4 2 minus IR. This another HPO4 2 minus IR. Sorry, next. So this unit, previous slide. This unit is linked to another unit by one water molecule, again linked with another water molecule. So it goes like a layer. So in each layer, the HPO4 2 minus ion is linked by water molecules. And this is one layer. There is another layer, the similar type of layer. HPO4 2 minus ions are linked by water molecules. The two layers are connected by water molecules. So these layers are connected by water molecules. So you have seen a layer is formed by hydrogen bonds between the two HPO4 2 minus ion. Interlayer connection is between the hydrogen bond between the another water molecule. So that means this water molecule has a different environment than this water molecule, W1 and W2. If you look at Raman data, you can see that two sets of Raman lines corresponding to water stretching frequencies. That is, one is corresponding to antisymmetric stretching, another is corresponding to the symmetric stretching. So a set of doublets are observed in the Raman spectrum in the stretching frequency region of water molecule. A set of doublets are observed in the stretching frequency region of water molecule. The reason is that you have two water molecules which are in a different environment, W1 and W2. One is responsible for the layer formation, another is responsible for interlinking the two layers. Next slide. So that is an SPS photo notation. This is a notation which is being used for oriented crystal measurements, that the crystals are prepared in a rectangular parallelepiped. That how do you prepare the crystals in the rectangular parallelepiped? So you have crystallographic directions, you know, A, B, C. So you have to cut the crystal with the crystallographic directions. This is possible in a case where alpha is equal to beta is equal to gamma is equal to 90 degrees. So if you have the crystallographic systems where alpha is equal to beta is equal to gamma is equal to 90 degrees, we can cut the crystal in a form of a rectangular parallelepiped with its edges parallel to the crystallographic directions. For other type of crystals, there is another technique. That's a different one. I will not be explained to you because it comes only on specific cases. So that's a specific problem. So wherever you have a tetragonal, orthorhombic, and cubic crystals, there is no problem. We can just cut the crystal with its edges parallel to the crystallographic directions. So if you cut the crystal, so you have X direction, that's the direction of the incident beam. Y is the direction of the scattered beam. This refers to the state of polarization of the incident beam. Again, I told you the analyzer, which is parallel, analyzer axis parallel to the Z direction, analyzer parallel to the X directions. Now, if you have ZZ, that is, this X tells the direction of the incident beam, Y tells the direction of the scattered beam. First Z tells the state of polarization of the incident beam, and the second Z tells about the state of polarization of the scattered beam. So you have ZZ and you can have ZX. See, you know that the crystals are anisotropic. So just in the same incident direction and the scattered directions, if you put the analyzer axis, you have ZZ component and ZX components. Okay, next slide. Next slide, please. Okay, I am trying to tell you the oriented crystal measurement because now people are working on films. They should understand when the film is prepared on a particular crystallographic direction, which are the Raman modes are active, which are the Raman modes are not active. So sodium lanthanum molybdate crystallizes in the scheelite structure. The space group C4H I41 bar A. The C4H, this is what a spectroscopy uses, that is called Schoenflies notation. C4H, it tells the Schoenflies notation. I41 by A, it is the Hermann-Magwin notations. Most of the people will be knowing the crystallography notation, that is I41 by A, that is the Hermann-Magwin notation. So the same structure, one corresponds to a spectroscopic notation. One is used by spectroscopists, another is used by the crystallographers. So it is a body-centered tetragonal lattice because I refer to the body-centered tetragonal lattice. So because unit is 2, it has 2 molecules. That is all I tell that it has 2 formula units. Now because it's a body-centered, so number of formula units, the perimeter cell is 1 because I here is equal to 2. So there are 3n minus 3 optic phonons because in the molecules, gas phase and the liquids, I said 3n minus 6. That's for the free molecules. So when it crystallizes, we have to look at them. The phenomenon, the feature is different. So now here is 3n minus. So in this case, we have is a 1 formula unit. So 5 into 12, 5 into 2, 10, 12. Then 12 into 3, 36, 36 minus 3. So now there are 33 optic phonons. This 33 optical phonons can be distributed into tau into 3Ag plus 5Ag, 5Ag plus 4Au plus 3Bu plus 4Au. So most of the people working on materials research, when you look at the Raman data for material, then you go back, you are going back to a paper where in which some Raman data is available. Sometime in some of the papers they give it as tau is equal to plus 3Ag, some distribution they give. This distribution is nothing but a group theoretical analysis based on a standard process which is called given in 1972. G. Fatale. It's a correlation method. It's a very simple process by which one can evaluate the distribution of various fundamentals in your space group. Here the space group is C4H, that is the point group symmetry C4H. So you can see that these are all distributed in various species of the C4H point group. The G subscript, the species with the subscript G are Raman active, the species with the subscript U are infrared active, but BU is infrared inactive also. B is neither Raman active or infrared active, it is highly inactive mode. So these all things you can deduce from this correlation. Next slide. So that I told you, you have the character table for C4H point group. You forget about all these things. What you have to import is this column and this column. So you have x square plus y square, z square, x square minus y square, xy, xz, yz. So this all will come, this x square plus y square, z square, they all come into the G species, Ag, Bg, Eg. Okay, Eg is xz, yz. Whereas this is AU, Z and EU is XY. So this character table tells that AU, BU, EU, BU does not have anything. BU does not have anything. That's what earlier I said when the previous slide. BU is inactive both in infrared and Raman. So once you know the character table, you can see that whether the species is Raman active or infrared active. So the symmetries of the Raman active modes in different orientations of the crystal, you can identify. So that's a matrix representation that is given by Loudon. He has done this work in 1964 for all systems. All systems he has worked out the Raman tensors form for Raman scattering cases for the C4H system. So for C4H system, he has worked out for AG species, this is the matrix representation, BG species, this is a matrix representation, EG species, this is a matrix representation. We not worry about all these things, it's very simple. Here is the diagonal elements, others are 0, 0. See this diagonal elements A, this is X, X, Y, Y and Z, Z. So AG, if you look at, you have XX and YY and Z, Z. If you look at BG, you have XX and YY and you have XY and YX. So XX minus YY and XY and YX. So here both are the same, here they are different. Here it's the same, AA is same, here the sign is different, here the sign is different, here the sign is same. Now here EG, you have XZ and ZX are the same, and YZ and ZY are the same. And here also you have same, because it's a doubly degenerate, it has a negative sign and a positive sign and positive sign. So if you have AG species, within the bracket you have ZZ you will have ZZ, then BG distinguish, you will have XY, EG if you want to have XY, you have XZ and Y, because XZ and YZ. In BG mixed you have had XX and YY. Suppose you have a mixed combination for AG and BG, you will have both XX components and YY components. So this is a very simple model in which we can look at for the Raman tensors. Next slide. Next slide. Next slide, please. Okay. So this is the correlation method. So in this factor group, suppose in the AG species, you will have nu 1, nu 2. That is that we have put molybdate ion, 4 normal modes of vibrations, nu 1, nu 2, nu 3, nu 4. The nu 1 in AG at 890, nu 2 at 317. Suppose if you look at BG, you have nu 2 component, nu 3 component, nu 4 component. But in AG you have a 317, in BG nu 2 occurs at 328, and the nu 3 occurs 830, nu 4 occurs 374. Whereas in EG orientation, the nu 3 occurs 794, not at 830. Nu 4 occurs 386, not at 374. Next slide. Next slide. So if you look at this AG spectrum, you will have nu 1, nu 2, 890, 370. What is AG spectrum? The incident beam direction is along the X direction, scattered beam is collected along the Y direction, and the state of polarization of the incident beam is Z, and the orientation of the Z axis along parallel to the Z axis. That is Z. Now, if you look at the Z is the direction of the incident beam, Y is the direction of the scattered beam. Now you have XY. That is, X is the direction of the analyzer axis parallel to the X axis, and Y is the direction of the polarizer axis, that is, it's parallel to the Y axis. No, it's the XY component, and the AG. See, if you look at Z is at XY, I used incident beam direction is different, scattered beam direction is different, and the polarizer axis, the analyzer axis orientations are different, but you could see that common lines are occurring at different frequencies. They are not occurring at the same frequency. You can see one at 890, 370, and another is 328, 830, 374, 794, 386. So if you look at, if you simply ask, I have a crystal, what happens if I just change the orientation on the measurements? Because the orientational measurements is very important, because the system is anisotropy, and because of the orientational measurements, you can say that molecular polarizability or the electronic load, which is still is different. So the frequencies are different, or the Raman tensors are different. So different orientational measurements, you can see particular modes are allowed, particular modes are not allowed. Even that mode is allowed, it appears at a different frequencies, because it splits into the components. Next slide. Okay, next, previous slide. So now AG occurs at 890, 370, nu 1, nu 2. Here 328, 830, 374. Now I measured Z, XX, Y. That is, Z is the direction of the incident beam, Y is the direction of the scattered beam. So I made XX component. Now I see that the spectrum contains all the 890, 317, 328, 830, 374. So 317 and 328, they are the split components of the nu 2 mode, and 374 is the one component of the nu 4. So nu 4 component is split and nu 2 component is split, but one component is appearing in one orientation, another component is appearing in the another orientation. So this is an example, very clear example, where you can look for orientational dependent Raman measurements. Next slide. So first of all, people working on materials, you should know on which orientation you have prepared the material, Once you prepare the material on a particular orientation, you must know which are the Raman active tensors, tensor components. If you know the tensor components, you know what type of frequency or what is the active component appearing in the particular orientation. Then I will go with the small examples. So liquids, we know that molecules are less tightly bound. The molecules are free to move. Molecule exert a force on another. Balakumar, shall I break or I can continue? Balakumar?
Sir, we can continue, sir. Sir, we can continue.
Okay. Molecules are less tightly bound. Molecules are free to move. Molecules exert a force on one another. Like classification of liquids, previous slide. Polar liquids, non-polar liquids. Polar liquids, you have protic solvents containing hydroxyl group. Aprotic solvents does not contain hydroxyl group. Acetonitrate. Non-polar liquids, zero dipole moment. That is your benzene. Next slide. Next slide. So binary liquid mixtures, you have mixture of two liquids. The solvent liquid present in the larger proportions. Solid molecule is the liquid present in a smaller amount. So you can vary the combinations when you mix the two liquids at various combinations. Sometimes one liquid will be the solvent, another liquid will be the solvent, then it will be reversed. So altering the composition of the one of the components, one can change the solubility, polarizability, viscosity. This is simple macroscopic signature which you look at it. But what do you look at, what do you see generally is ignoring the intermolecular forces. Just to measure the viscosity as the macroscopic property, you measure the solubility, just to say the macroscopic property. But you have various types of intermolecular forces existing between two molecules. The molecules are bound together by intermolecular forces. This intermolecular force can be dipole-dipole or dipole-induced dipole, induced dipole, induced dipole, and a hydrogen bonding force. Next slide. So Raman spectroscopy can be just used to find the signatures in a binary liquid mixture. Analysis of the wave number shifts and the line profiles in the neat liquid as well as the binary mixture will give you a probe or an understanding or investigating inter and intramolecular interactions. Because what do you see, the viscosity and polarizability measured by conventional method, you are simply ignoring the inter and intramolecular interactions. Suppose you want to understand the inter and intramolecular interactions, one can make use of Raman spectroscopic technique. So what is important is because the frequency changes and the line profile changes with respect to the constituents. One simple example is the 4-methoxybenzaldehyde. That is liquid, so you use the different solvents, propanol, acetonitrile, and benzene. Next. Next slide. Next slide, please. Kumar. So this is anisole, that is the same material, which is a different nomenclature, we just use it. So here it is a monomer, and this is a monomer, there is a dimer. So in the dimer formation, there is an intermolecular, that is between the two molecular units, there is a hydrogen bonding. So now, if you look at the Raman spectrum, you have two Raman lines. One is at 1684, that is a hydrogen bonded carbonyl group. Another is on a free carbonyl group. So you can have a monomer or a dimer in the same, because it's liquid, it forms a dimer forms and gets dissociated. So there's an equilibrium of dimers and monomers. But if you look at the hydrogen bonded is more than the free molecule. So more number of dimers compared to the number of monomers. So the dimers are predominating than the monomers. That is why you have a hydrogen intermolecular hydrogen bonded carbonyl frequency. So one is 1684, another is 1705. Next wave number. Next slide. So just to see the propanol. So you see, if you look, the C is the neat. You can see the intensity decreases, but also frequency changes. And if you look at the changes, it may be linear or it may not be linear. It may be linear or it may not be linear. So I just formation of the hydrogen bond, that is between carbonyl oxygen, that is in a monomer, there is one carbonyl oxygen, one carbonyl group is there. That carbonyl group makes a hydrogen bonding the propanol. Okay, that's hydrogen bond formed. Now you dilute it, that is more propanol molecules are coming inside. So degrees of the concentration of the anisaldehyde. So the probability of the hydrogen bond formation, that is because you have more number of solvent molecule and the solid molecule is less. So that is the anisaldehyde is more, the anisaldehyde is less, and propanol is high. So there's a very high probability that the anisaldehyde can go for a intermolecular hydrogen bonding with a propanol molecule. Because propanol molecules are, it is being surrounded by more number of propanol molecules. So the probability of formation of hydrogen bond between the anisaldehyde and the propanol is more. So that decreases the hydrogen bond. That decreases because more hydrogen bonds are formed. That is probability is high. So it basically decreases the hydrogen bond strength. Then it forms and dissociates. Here, it's almost it formed. The bond is formed. So it decreases the bond strength. That is why when on diluting this anisaldehyde with more propanol molecule, the lower wave number 1 shifts to the hydrogen bonded frequency shifts to the lower band. It shifts a downshift. It shows a downshift. Whereas in the benzene and other case are different. Next slide. Next slide. So you can see that previous slide. In benzene, this line width. So here it's maybe next slide, please go. Post aldehyde. Okay. Now earlier I have told you this depolarization ratio, I parallel and I perpendicular. So rho is nothing but I perpendicular by I parallel, the depolarization. But in this case, I have specifically told you that either you do it in the parallel measurements or in the perpendicular measurements, there will be no change in the Raman shifts. That is, the frequent wave numbers occurs at the same position. Either you do it in the perpendicular measurement or in the parallel measurements, the wave numbers do not get changed. So that is why I said here is 459 like that. Next slide. Next slide. Next slide. Maybe that is. Okay, so this slide. So this is the slide. You can see that either you do it. This one is the weaker hump. It is isotropic. That is I perpendicular measurements, and two equally probable peaks, strong peaks. That is the anisotropic component. So isotropic component and the anisotropic component both are occurring at different frequencies. So earlier I told you the depolarization ratio measurements you should get at the same wave number, but here we are getting at the different wave numbers. That's a shift. So how it occurs? Because whether the theory is wrong or your interpretation is wrong or the experimental observation is wrong. So let me go. This is the experimental observation. Okay, previous slide. Okay, so if this is 4-ethoxybenzaldehyde, so it can have as a monomer or it can have a dimer. So you have a monomer and also you have a dimer. So dimer formation is there and a monomer is also there in the given medium. Next slide. Previous slide. Okay, so when dimer is formed and the monomer is there. Okay, that is what I said. There is a local order. Because of the local order, a pair formation is created. So when a pair formation is there, there is a resonance coupling between the adjacent vibrating molecule. So when the resonance coupling occurs between the adjacent vibrating molecules, so just something like your beat, that is, one goes to the higher frequency, another goes to the lower frequency. So because of the resonance, it splits into two components. One goes to the higher frequency, another goes to the lower frequency. Okay, when it goes to the higher frequency, the state of polarization is different. When it goes to the lower frequency, the state of polarization is different. So both components are not having the same state of polarization. The state of polarizations are different. So that is why, next slide, next slide. Next slide. That is why you have an anisotropic, one spectrum, that is a profile with the indents and a shoulder isotropic components. The anisotropic component, they are occurring at different frequencies. That is because it comes only because of the resonance interaction between the two neighboring molecules or when a pair is formed. Next slide. If you introduce acetonitrile, a solvent, it comes like this. So these are all like Gaussian software. Next slide. See, when I say that acetonitrile is introduced, it spoils the pair formation between the two molecules. It spoils the pair formation between the two molecules. So when the pair is formed, you have a resonance coupling, and the pair formation is distorted by an acetonitrile molecule. Next slide. Methanol. Methanol also, it spoils the pair formation. Next slide. DMF. DMF also spoils the pair formation. Next slide. So benzene, it does not spoil, but there is every possibility that because it's a dipole, because it's a non-polar system, it does not have any dipole moment. Or if this system has these pairs have a very high dipole, they can induce a dipole on the benzene system. So here the pair formation breaking will not be as you have at acetonitrile, DMF and methanol. Next slide. So you can just derive the peak position, and also you can derive the intensity ratio of the carbonyl groups, that is hydrogen bonded and the free, and you measure with respect to the corresponding intensity ratio of the liquids. They all show a different signature. See, in the benzene, you can see that the block dots refers to the frequency shifts, whereas these white dots corresponding to the intensity ratio. But you see the trend is different because benzene is a non-polar solvent. The mechanism which you have is entirely different. So here you can see the opposite signatures, opposite trends, whereas in methanol, it has the same trend, whether you have the intensity ratio for these two lines or the peak position. The trend, you say the intensity ratio and the peak position remains the same, whereas in the benzene, it is different. Next slide. Next slide. Next slide, please. Next slide. Kumar, next slide. சொல்லுங்க Balakumar. No problem. Hello.
சார் வந்துடுறேன் சார்.
Okay.
It's a problem in your slides again. Not open your slides. One minute. இந்த ப்ராப்ளம் இருக்கு நமக்கு. அண்ணாமலை உங்களுக்கு ஒரு பிபிடி அமைச்சிருக்கேன் பாருங்க, அதை ஓபன் பண்ணி ஷேர் பண்ணி பாருங்க. நீங்க உட்கார முடியும். Sir, I asked my student to share the slide because I have some problem. ஷேர் பண்ணிட்டு அந்த ஸ்லைடு ஃபார்ம் பண்ணலாம். கரெக்டா? Yeah.
Okay, fine. Now I can speak now.
Yes, sir.
So now it's a benzene. So now this pair formation is distant, but it is a induced dipole induced one, or a dipole induced dipole force. But the disturbance, the pair formation prevented here, but it's not as like your earlier cases where your acetonitrile, methanol and DMF, because there certainly an intermolecular hydrogen bonding is formed between the solute and the solvent, but here the separation occurs, but not as the case. Next slide. Next slide. So now you can see that we measure the width, spectral line width, whereas in methanol, it just gradually comes down. Whereas if you look at DMF, it goes down and then increases. It's a very peculiar case because what generally people observe is in a Gaussian profile, but here what you have seen is an inverted profile. So it all begins of the intermolecular interaction, because DMF itself can form a dimerization. So once the solvent concentration increases, that signature predominates. So that is why that's why earlier I told, whatever you have a minor liquid mixture, what you measure the polarizability or the viscosity, these are all just to measure the macroscopic signature. But if you look at the microscopic signature, you see that the line width, common line width, just decreases then increases with a mole fraction. Okay, with the decrease in the mole fraction of the probe molecule. Next slide. Next slide. So now you see that, okay, this is fine. Now it's like, okay, fine. Now you have a DMF I put some stars here and there. Okay, now the separation between the hydrogen bonded and free carbonyl position in binary mixtures for varying concentrations. Now at 0.7, that is the one particular concentration, you say this one, and you say that it shifted to 20, whereas in the other cases it has called come down. So the separation between the hydrogen bonded and the carbonyl free carbonyl group, because you have shown isotropic component and the anisotropic component, you have two peaks. In isotropic, one strong peak and a shoulder, another is equally. So the difference between the two components, the separation between the two components varies with the various solvents. It varies with the various solvents. Because when the solvent concentration increases, the separation between also is it decreases. Other cases, it shoots up. That is very interesting. That's why I said you are looking at a microscopic signature. But of course, we have given the explanation, but just to show you that there's a data which is available that even the frequency separation between the hydrogen bond and the carbonyl group cannot be the same. The separation cannot be the same when you vary the solvents or when you vary the solvent concentration. Okay, next slide. So now this is what how long I can take, Balakumar? Maybe another half an hour? Maybe slides, you pass it on. You place slides, you pass it on. Slides, you pass it on. Next slide. Next slide, next slide. You just to change, just to change. Next, we switch on. We'll say go because we'll go to materials. Materials. Okay. Now it is 4:30. Next slide. Goes change on. Okay, micro-raman. So micro-raman spectroscopy, it's a technique which is used to see the crystallinity of the film you prepare. And you are measuring at the submicron level. So when you measure the submicron level, you want to understand the microcontaminations and the carrier concentration and the diffusion. And also you can try to measure the lattice strain measure. You can do the lattice, we can understand the lattice strain. So now people working on materials research, all you prepare a film on substrate, deposited the material is deposited on substrate, or you pay a heterojunction. So you want to understand what is happening around it through micro-Raman measurements. So you want to understand crystallinity, you want to see what is happening in the submicron, what is happening to the lattice mismatch or the lattice strain. Next slide. So this is SNO2, it's a rotile structure. As a 6-unit cell, you can have 3n-3 optic phonons. I told you, you can see the distributions to the space group, and of these 18 modes, 4 modes are Raman active, A1G, B1G, B2G and EG are Raman active. 2 modes A2U and U are infrared active. The 2 modes A2G and B1U are silent. This, of course, you need not look at it, you can know the character table for this. You can just find out that these modes are Raman active, these modes are infrared active, these modes are neither active in any of this. Okay, next slide. So this is an optical image of SNO2 nanopowder. First, A is as grown sample, B is annealed at 600, and C is annealed at 800, and D refers to the annealed at 1000 degrees. So you can see that you can see in the first as grown, you can see some crystallites here and there, and you increase the annealing temperature, you can see the surface becomes more smooth. That is, what is happening is that initially it's a crystal, but then it's a disorder or the discontinuity. So then on annealing, you see that you are trying to improve the quality of the crystallinity. So this is an optical image. This is just an optical image. You can see the surface is smooth and appears to be homogeneous when you look at the annealed at 1000 degrees. Next slide. Slide, please. So you look at, So the room temperature, this is weak, 600, 800,000 degree. You can see that the A1G mode becomes more intense. So 633 Raman line becomes more intense. So then when you look at after annealing, what happens? You don't see the new band, almost the same bands. There is no shift in the lines. So it says that the structure is not distorted. The only what you do is you tune the crystallinity. So when the if there is a new peak comes or the shifts or the asymmetry, then it will tell that there's a phase change occurs. So signature remains the same. The Raman lines remains the same. Only thing is the lines, the intensity starts to grow and the line width starts to decrease. Whereas if you look at it, it becomes more and more narrow. Compared to this one, it's a very sharp peak. So the intense but narrow. That means the crystallinity is tuned. So what conclusion you can say that, as you see from the optical image, on annealing, or you basically increase the temperature, it tells that the crystallinity is tuned, which is reflected from the very sharp Raman line associated with the A1G species. That's at 630. That is what the insert I also showed in the insert. How it does. Next slide. Next slide. Next slide, please. So this is semi-insulating gallium arsenide, the substrate, on which enriched gallium arsenide or p-rich gallium arsenide, and there is a metal electrode, and that is the metal electrode, which is what we have seen it in the semi-concentric circle and here and there. So you have a substrate and the N plus gallium arsenide and a P plus or enriched gallium arsenide or p-rich gallium arsenide, and you have a metal electrode. That's what I put, N plus gallium arsenide, enriched gallium arsenide deposited on a semi-insulating gallium arsenide. So, next slide. So the SPS photo notation, that's what I told you, alpha ZZ, alpha XX, alpha ZX. So in this particular orientation, which type of Raman tensors are allowed? That is group theory, theoretical methods tells you. Now is there, in this back scattering geometry, LO phonon is there and a TO phonon is there for gallium arsenide. That is LO at 292 and TO for just to take a polycrystalline gallium arsenide Raman spectrum. You have two lines, one associated with the longitudinal optical phonon, another associated with the transverse optical phonon. Or the just a Raman spectrum of the gallium arsenide samples will have to show two lines. One is LO, another is TO. Okay, fine. Now that is the basic one. Now I do a oriented crystal measurements. That is, I go for parallel or perpendicular measurements. Next slide. Next slide, please. Okay. So in the back scattering geometry for Z and Z bar, that is Z is the incident beam direction, Z bar is the scatter beam direction. That is the back scattering geometry. So in the back scattering geometry, LO mode is allowed, TO mode is forbidden. That is, I told you in the sodium lanthanum molybdenate case, in one, depending upon the orientation, the Raman frequency, the modes will be appear in particular orientation, may not appear in another orientation. Even the doubly degenerate mode, it can appear in one orientation. Another one component appear in one orientation, another component appear in the other orientation. So here in this case, this back scattering geometry, one mode is allowed, another mode is forbidden. That you have to see only 292 Raman line, should not see 268. But here in this case, 268 more intense than the 292. The forbidden mode is more intense than the allowed mode. So what is very interesting. So then you anneal it. When you anneal it, still the intensity of the forbidden mode is more intense than the allowed mode. But the ratio has fallen down, but still it is greater than 1. Next. Next slide. Next slide, please. So so when we go for the P plus, then P rich gallium arsenide. So in the P rich gallium arsenide, this one, the this one, it shows still the forbidden mode is more intense than the allowed mode, but when you annihilate, the ratio becomes less than 1. So in a p-rich situation, when you annihilate, what happens? The forbidden mode is less intense than the allowed. Make a ratio between that forbidden with respect to the allowed, the intensity is less than 1, whereas in this case the ratio is greater than 1. Next slide. Next slide, please. So next, previous slide. Okay. So the observed features tells that it is a characteristics of the crystalline, because you have seen LO mode and TO mode. Okay, fine. Both peaks are there. You are seeing. So you have a modified first order peaks. That is because the forbidden mode is also coming. So that means the material is partially modified. So the Raman signal tells that the signal has come out from a set of confined but ordered regions, but it is otherwise embedded in a disordered region. So you have an ordered one, but regions embedded in an otherwise a disordered region. So you can just scan on the surface, and in which region you are able to see that forbidden mode is less intense than the allowed mode. So what just general macros over the surface, we just tell that it is now what you say a set of confined but ordered region, but it is embedded on the otherwise a disordered medium. So TO lines observed for all the samples, that is the forbidden mode comes in all the regions. That means the non-conservation of wave vector is not followed. That is wave vector non-conservation comes. So you have a creation of a phonon which becomes transposed due to the change of wave vector with respect to the polarization produced by the scattering from a disordered lattice. So yeah, from the disordered region, a phonon is created which becomes transverse and due to the change of wave vector, because you have a disordered lattice and a polarization signature which comes, which change the wave vector, then it makes the phonon status also from a to be a transverse phonon. And also you can see the, because of the disorder lattice, you can also see the second order modes are coming. That is also indicative of induced lattice damage. Next slide. Next slide. So introduction of deep level states which trap charge carriers can be the source of damages. A layer to fit the damage is expected. N-type is found to be more susceptible to the sputtering damage. Changes in sheet resistance of N-type and P-type, indium gallium phosphide or indium gallium, this were gallium arsenide, exposed to the organ plasma. That is, you are very particular that the charge carriers are just moving and they are being trapped, and that trap state is responsible for your observed signatures. So when charge carriers move, the sheet resistance, how it changes the N-type and P-type. So you measure the sheet resistance and make a correlation between you and Raman. Next slide. Next slide, please. The ratio. Previous. You can see that previous slide. So for intensity T1 ratio of ITO by ILO, the P plus gallium arsenide, if you see from the surface, it goes down. Depth axial displacement delta, that is, you are just penetrating, you are collecting the samples from the surface down about 6 to 7 nanometers, whereas here it just to see it comes from 2.2 to 1.2, whereas it comes from 6.7 to 0.4. Here it is low, but here it is always greater than 1, here it is always less than 1. But if you see the variation from the depth, when it goes, when you make a penetration depth measurements, because you can move the beam, the variation to the z-axis, then we do the measurements for the z-axis, then you see that ITO by LO, it is less than 1, but in P plus, it reaches a very small values. So the surface to the depth of the incident light intensity. So you measure the Raman intensity, observe at each axial depth and absorption. Okay. Next. Next slide. Next slide, please. The next slide, please. Next. Just jump it up. Just next slide. Next slide. Next slide. Next slide. Okay. So now you can measure previous slide. Previous slide. Previous slide. Previous slide. Previous. Not just fast on previous slide. You go. Previous slide. Oh, previous slide. Okay, and then next slide. This is okay. Previous slide is one. Just I have to. Okay, now is it next slide. Next slide. Okay, so it's a silicon implanted gallium arsenide. So next slide. You just come down. As I told about the gallium arsenide 29. Next slide. Okay, now for various doses, and if it is 1 meter to the power per square centimeter, in that material annealed at 473 Kelvin up to you have annealing temperatures, then you can see that the intensity starts to grow at higher annealing temperatures, and of course suddenly the area under the curve will also increase because your intensity has increased. So the ordering and the alignment of the mesoscale happens at annealing because you damage the surface, but after damaging you anneal it, so you have an alignment of mesoscale crystallites. So the decrease of RTO by RLO, increase in the penetration length, that is it decreases, that means the scattering volume associated to the LO mode has increased, and so that is why the ratio has come down. Then the maximum because once you measure the penetration depth measurements, you can see that the maximum damage occurs at the surface because you impinge it, so the damages occurs at the surface. Next slide. Yeah. So previous slide. So there's a relationship between the Raman shift and the biaxial stress. Delta omega L, delta omega T, delta omega L corresponds to the Raman shift associated with the longitudinal mode. Delta omega T corresponds to the shift TO mode because you have a Raman spectrum of a gallium arsenide before implanting and after implanting, then after annealing. So first raw, either pure or undisturbed gallium arsenide, then you damage the surface by implantation, then you anneal it at various temperatures. So first you taken as the reference one, for after every change you make it, you measure the Raman shift. So delta omega L corresponds to the Raman shift for the longitudinal optical mode, delta omega T corresponds to the TO mode. The negative sign, it tells the positive line shift induced by the compressive stress. Okay, it moves the higher frequency. Next slide. So delta omega, so at 4 to 1. So when it comes to delta omega reduces because we are moving more to the crystallinity, because more damages happened, and but the annealing is less because at lower temperature, so the rearrangement of the crystallites will be less, so but the shift will be high. So you can see delta omega is 4 to 1. Then you can see the biaxial stress decreases the increase in annealing temperature. Then from the biaxial stress, you can calculate the carrier concentration. Then you can calculate the omega p, that's the plasma frequency. How the carrier concentration, because these LO phonons interact with the free charge carriers, that is, you have a surface plasmons. So these phonon modes, these phonons interact with the surface plasmons. So there is a coupling. So that's what they call phonon plasmon interactions. So this phonon plasmon interaction will cause a change in the line profile. That is, the line profile will has to take care of the phonon plasmon interactions occurs. So the line shape or the shape will all help you to measure a direct measurement of the carrier concentration. This is a numerical relation we can calculate. In fact, people have done on the carrier concentration distribution on a surface. Next slide. So then people try to estimate the phonon correlation length. So the phonon correlation length 470 36.9. When you come to 673.2 is the decreasing length that is terminated. You have nice, well-defined slides. The grains are formed because when have more correlation length, that is, suppose you say 36.9, so it propagates more, and you don't have a spatially well-defined region. When the correlation length is less, that means you have spatially well-correlated region. So the correlation length becomes more and more smaller, means then we have a well-correlated signatures. Next slide. The gallium nitride. Next slide. Here also you can see for the orientations which are allowed. So in the XY orientation, you have E2 mode, that is at 567, and XX measurements you have 734 and 567. Two Roman lines will come. Next slide. Next slide. So again, I tell you the damage with respect to the gold deposition. Next slide. Next slide, please. So again, I tell you the width of the E2 mode reflects the crystallinity. Previous slide, previous slide. So then you can say the frequency increases. It's a compressive stress. It decreases the tensile stress. Then the several causes for the lattice strain, lattice mismatch, lattice structure disorder, neighborhood, that is the native defects or the defects incorporated by the impurities, they all will create that lattice strain. So the lattice strain can be estimated by the phonon frequency shift. Okay, next. The LOPC mode, longitudinal optical phonon coupling mode. That is what I said, the collective excitations of free carriers interact with this slide. This is okay. So now you can say this L plus, that is positive, that is a coupled mode. L minus is the negative coupled mode. Omega T, omega L is uncoupled A1 TO mode, A1 LO mode. So these modes, LO or TO, they can couple with the plasma modes. Then you have L plus mode and L minus mode. From the L plus mode frequency and L minus mode frequency, you can evaluate what is the carrier concentration. Slide. So you can find out what is omega P. So the numerical relation from omega P, you can calculate omega plus. Once you know the omega plus, you can calculate the carrier concentration. Next slide. So the indium gallium, indium gallium nitride on gallium nitride, that is on the silicon substrate. Indium gallium nitride on gallium nitride. Then the whole nano column is grown on silicon substrate. Next slide. So this is an optical image. Next slide. So you can have a group theoretical calculation for gallium nitride 567. Okay, next. So you fit it with the Lorentzian fit for this 568 Roman line. Okay, so once it becomes narrower, then it becomes the reflex crystallinity. Next slide. So optical phonons, the optical phonon propagates in the lattice of a single crystal as a wave. So it propagates. So it exhibits dispersion depending on their wavelength or equivalent with their wave vector in the Brillouin zone. Momentum conservation selection rule determines the region of the Brillouin zone assessed. So you have an optical phonons, it propagates in the entire crystalline lattice as a wave. and it shows the dispersion depending upon the wavelength or wave vector in the below and so. So they have a momentum conservation. But these are all applicable only for optical phonons which are close to the zone center, Q is equal to 0. So Q is equal to 0 selection rule essentially a consequence of the infinite periodicity of the crystalline lattice. Now the periodicity of the crystal is interrupted when disturbed. Grains are formed when the periodicity is disturbed. So the relose relaxed, the Q is equal to 0 is not valid. The phonon propagates gets disturbed when a grain boundary is encountered. So that is what I earlier said, phonon correlation. So the phonon correlation determines the propagation of the phonon and the grain size. So the phonon propagation gets interrupted when a grain boundary is encountered. That's why a phonon correlation length. I told a phonon correlation is nothing but if you look at a sphere, you can tell that what should be its radius, like that. Next slide. So for a part, previous slide. Particle size phonon wave function. The previous next slide. Phonon wave function must decay to a very small value close to boundary. Restriction on the spatial extent of this wave function allows phonons corresponding to the selected wavetors to be sampled by the Raman scattering. So that is a grain size. I say the particle size deep. So that will tell you the value when which is phonon wave function decays to a very small value at the boundary. Next slide. Next slide, please. So the phonon correlation model is applied for E2 mode of gallium nitride. Next slide. Next slide. Next. Okay, so this is a numeric. This is the expression. So based on the expression, the intensity plot is made. That is, the dark line is experimental, red line is theoretical. So for the grain size, what do you say is the D value, we try to fix it for a particular value of 160 nanometer. The theoretically simulated Raman profile matches with the experimental profile. So you have to go to a situation, you vary the parameter so that for actual diameter of the nano column, you have some X value. When you fix that X value, that simulated Raman profile should overlap or should match with your experimental Raman line. So you have to continuously try. Next slide. Next slide, please. So we try for various nano column size. L1 is 60 nanometer, L1 is 80, 100, 120, 140, 150, 160. So you can see that how the profile changes. These are all simulated theoretical data. So when it comes to L is equal to 160, it shows a very perfect profile. So whether it's L1 is 150 or L1 is 160, you have to superimpose on your experimental observed data. When L1 160 matches with the experimental observed data, this previous slide, you can tell. Previous slide. No, the next. Okay, so previous slide. Previous slide. Oh. Previous one. Okay, now you have fit. That fit value is L1 is 160 nanometer. Now the nano column, the diameter of the nano column is 160 nanometers. Okay, now we have found out. Next slide. Come down. Okay, now you are just one method. Next, you come. So here also you just try to fit in. Next slide. Here also you can calculate the. Now you can see that it just starts from 3 nanometer to 100 nanometers. So you have to see for which value of this profile, for which value of the column, the measured, the theoretically predicted profile matches or superimposes on your measured data. Next slide. So it comes to 20 nanometers, 15 nanometers, 15 nanometers. So 3 different materials. So in 3 different cases, we try to superimpose the best fit. What is the best fit we can have for the data? So in one case, it tells the column size. It's 20 nanometers, 15 nanometers, 15. Next slide. So you can tell the free carrier concentration. Next slide. So you just again, because you evaluate a carrier concentration, that also you try to fit in with your experimental data. So when you have the experimental shape, line shape, and the theoretical line shape. This theoretical line shape matches for the condition for when the carrier concentration is 5.10^16 per cm cubed, and the omega frequency is 94 wave number. Or you just put it as n, then and later you deduce omega p. So for each n value, you try to find out, or once you know the column size or the wave number, you try to find out omega p and n. So you can theoretically predict the column size, theoretically predict the carrier concentration. Next slide. So this all for various samples we can do it. Next slide. Next slide. The Raman mapping technique. So Raman mapping is the XYZ direction, moving the sample to different points of excitation, collecting separate Raman vector. Next slide. Next slide. Okay, so you have a wafer and a material is deposited, that is and indium nitrate, gallium nitrate core shell that's deposited on this thing, and there is a void. You can see what is here in the red and dark regions. The red regions are the region in which you see this Raman signal from the material. Void, dark regions are the regions where the void, that is you are getting signal from the substrate, that is the silicon. So this body down you see the Raman replica of your optical image. This basically an intensity distribution. Take a Raman line and measure its intensity across the entire material. Whether you want to have data points, you want 200 data points, or you can have 400 data points. You can just measure, you can make a intensity distribution. Simply I can say that it is an intensity distribution or Raman replica, Raman intensity distribution of your optical image. Next slide. Again, next slide. Next slide. Next slide. Okay, so you have a D band. Stop here, stop. We have a D band and a G band. So you can measure the G band distribution. Actually, in principle, you are measuring the graphene distribution on the surface based on the intensity of G band and 2D band. Earlier I have seen the D band, the defect activated band, and here is a G band and 2D band. So various color, then you can measure the ratio and you can develop a histogram. From the histogram you can find out how the distribution is on the substrate, how the distribution of the graphene flakes on the substrate, or how the graphene flakes, suppose you have not deposited, suppose the graphene flakes are there, you can see how the graphene flakes you have synthesized or you have evaluated. So the histogram will help you. Basically, you just to make a Raman intensity distribution across the surface, either for D band, defect band, or G band and 2D band. Next slide. Okay, these are all you can do for various videos. I think I will conclude here. Balakumar,
Yes, sir. Yes,
Balakumar,
sir. Yes,
I
sir.
will I will conclude here. Now it is 5, and
Yeah. Yes, sir.
okay, any questions they can ask me.
Okay. Sure, sir. Participants, if you have any clarification and questions, feel free to ask that. Or if you can also send the questions through message chat box, I can also ask the question. And or if not, you can also send an email to staff.
Raining heavily in Madurai.
Oh, okay, sir. Okay, sir. If there is no question, you can. Any question from the participants? Sir, what is the formula for calculating the career concentration?
Like I showed you, no? There is a relation, there is a numerical relation from which you can calculate.
Okay,
Okay,
sir.
actually, these are all it's available in the literature. Okay,
Okay.
you have it. No, come down, come down, come down, come down, come down. Because it is Jagannathan himself have worked for the Gallimard when he was in Germany.
Okay.
So that is available in the literature.
Okay, sir. Okay, sir. I'll do this.
Yeah, but
But
what?
have you ever tried to calculate the career concentration for graphene?
Pardon?
Graphene, sir.
Graphene we have not done, but we can try. There is no issue at all.
Okay. So that
Yeah.
is what we are interested because when we integrate graphene with metal oxide,
Okay.
the band gap decreases and carrier concentration increases, and so that starts in turn, it is increase the photocatalytic activity. That's basically availability of more electron
Yeah.
for. So that maybe we
For
can like
transportation. For
yeah, yes,
transportation. For activity.
yeah,
Okay. Okay.
yeah.
Okay. Hmm. That can be done. That's may not be an issue.
Okay. Okay, I think the questions I think they will send. Uh, So, on behalf of the Nano Science Center and Omega, I thank you very much, sir, for an extensive talk on Raman spectroscopy, and especially the second part was very interesting for us. But we are all more working on inorganic material. So that part, the characterization in Raman, characteristics of nanomaterials, Raman scattering is a very interesting topic, and we look forward to work with you. And with
Thank
this,
you.
we can
Always welcome. It's always welcome.
finally we
My
can
pleasure.
close the session, sir. Thank you, sir.
Thank you. Thank you.
Thank you, sir. Thank you.